Engineers often need to work with mathematical models of a system's behavior, but sometimes it isn't feasible to develop the mathematical model from fundamental equations. In these cases, it's common to test the system and then use the measured data to develop a mathematical model. This process is commonly called curve fitting, and it's the topic of this lecture. First, I want to talk about the overall idea behind curve fitting. We're always going to start out with some measured data that's the result of an experiment, which is usually in the form of pairs of x and y values. As an example, this horizontal axis may correspond to temperature, and the vertical axis is the Young's modulus, or the strength of a material at that temperature. Now, this data may have errors in it, since no experiment's perfect, so we don't necessarily want to believe that every single data point is exactly correct. What we want to do is to create an approximation to the data that provides the best overall representation of all the data taken together. This straight line, for example, may best approximate this data set. Now I've got a good approximation to the overall behavior of the data, and I can determine the y value corresponding to any value of x that I want. Measured data is useful to predict a system's behavior only at the points where the data is measured. In order to analyze or design a system, we need to describe its behavior at all possible operating points. This requires us to develop a mathematical function that describes the set of measured data. That process is called curve fitting, since the mathematical expression is presented graphically as a curve. Since measured data is subject to errors, we may not want the curve approximating the data's behavior to actually pass through all, or even any, of the data points. The goal is more often to use the data to establish a trend or an overall best approximation to the data. In a typical curve fitting process, we have a number of measured data points, which are represented here as x-y combinations. Each data point has an x and a y value. So the first data point is at a point specified by x1, y1. The second is at x2, y2, and so on. Our goal is to use these data points to estimate a mathematical function that best describes them. First, we need to define mathematically what we mean by best. That way, everyone knows the rules associated with our choice, and our curve fit is unambiguous. In this course, we'll use what's called a least squares best fit of the line to data. We have to start out by choosing a shape of the curve we're going to use. In this case, I'm going to use a straight line. Now we need to decide how to represent the error between the data and the line representing the data. There are a variety of ways to do this. In least squares curve fitting, our error will be the square of the vertical distance between the line and the data point. So we'll define the vertical distance between the line and the data point at that value of x as the error in the estimate at that value of x. So the error at x1 is E1, the error at x2 is E2, and so on. Since we've chosen to represent the data by a straight line, its equation is y equals mx plus b, where m is the slope of the line and b is the y-intercept. We want to find m and b such that the sum of the squares of all of these errors are as small as possible. It's the line that gives us the least value of the square of the errors, hence the term least squares curve fit. Now let's briefly go over the math associated with this approach. The first step is to define the error at data point k, which is the difference between the measured value of y at the kth data point and the value of y that would be given by the curve fit, which would be m times x sub k plus b. Then square this error at each data point and add up all of these contributions to get an overall error between all the data points and the curve fit. Finally, choose values of m and b for this straight line, which minimizes this overall error, capital E. This step is mathematically kind of tedious, and MATLAB will do the work for us, so I'll gloss over the details here. Now I'll talk a little bit about using MATLAB to do this process. Remember that we have a bunch of pairs of XY data. If we plug each of these pairs of values into the equation of the straight line, we get y1 is equal to m times x1 plus b for the first pair of data points, y2 is equal to m times x2 plus b for the second pair, and so on. This set of equations can be written in matrix form as shown here. A vector of y values is equal to a matrix with a first column that's the x values and a second column that's all ones, times a vector containing the slope and the y-intercept of the straight line we're fitting to the data. So y1 is equal to m times x1 plus b, y2 is equal to m times x2 plus b, and so on. Now we have a system of equations of the form ax equals b, but now we usually have a lot more equations than unknowns. A system with more equations than unknowns is called an overdetermined system of equations. This can be a problem. Since our line will usually not pass through all the data points, this system of equations will probably not have a solution that satisfies all n equations. So overdetermined systems of equations don't generally have a solution without imposing additional requirements. Specifying that we wanted a least squares solution to the equations earlier provided an additional requirement that allows us to solve this system of equations. That brings us to using MATLAB to solve this system of equations. The backslash operator returns the least squares solution to an overdetermined system of equations. So next, I'll do an example of using the backslash operator to perform a least squares straight line curve fit to a set of data. The first thing to do, of course, is to create vectors containing the data. I've named them x and y. The other thing that's generally a good idea is to plot the data before attempting a curve fit. That can help guide you as to what to expect from your curve fit and what kind of line to fit to the data. To plot the data, I'll use plot x, y, RO. Data points are usually plotted without lines connecting them. You just put symbols at the data points. From the data, it looks like a straight line curve fit would be appropriate. Now I can create matrices that put the equations for the line in the form A times x equals b. The first column of my A matrix contains the x values for the data. The x data are in a row vector, so I'll transpose it to put it in the first column of the A matrix. The second column is all ones. I need the same number of ones as I have x values, so I can use the size command as an argument to the ones function. The second column then is ones of size of x transpose. The size command returns the number of rows and columns in an array, and the ones command has the number of rows and columns as its input arguments, so they work well together here. My b vector is just the y values of the data points, so I'll set b equals y transpose, since b needs to be a column vector and y is a row vector. To solve for the coefficients in the straight line, use the backslash operator. COEFS equals a backslash b. With the form of the A matrix I used, the first element in this COEFS array will be the slope, and the second element will be the y-intercept. The last step will be to plot the line and the data together to make sure that my results make sense. The y values of the line at the same x points of my data can be created with y underscore fit, which will contain my curve fit, equals COFS of 1, the slope, times x plus COFS of 2, which is the y-intercept. To plot the line, I can hold my previous figure and then type plot of x, y underscore fit. That results in a straight line, which seems to approximate the behavior of the data fairly well. MATLAB has built-in functions to perform polynomial curve fitting. This set of tools includes a variety of other functions relative to polynomials. In the next video, I'll talk more about these types of functions.